And I guess we are now.
Oh, wow, just on time. Welcome, everyone. Thanks for being here tonight. Thanks to the co-working login, Alessio and Federico, for hosting us. We are really happy we have Vaughn Vernon giving a talk tonight at our meetup. This is a series of meetup organized by Avanscoperta. Some of you already know us, some of you don't. We organize workshops and training courses, but also do some consulting in companies or do on-site training. These are for developers, team managers, etc. And we also organize meetups whenever we have a good speaker in town, like the gentleman here today. We are gonna ask you to fill in one post-it, surprise. Sorry, it's not orange, but we might sort it out by the time I give it to you. With your name, surname, and email address, we're gonna do a raffle for you to win. Da-da! So, up to you if you wanna do it, but I guess you will want to do it. And now over to Vaughn Vernon.
Thank you for attending tonight, and another thank you to Alberto and Avanscoperta. I want to see a show of hands. Who has not been to an event of Avanscoperta? I don't mean a meetup. I mean a class. Who has not been there? We have some work to do. So yeah, you're in for a real treat if you attend one of their workshops, classes. It's top quality. Yeah, I promise you that. So I hope you look into that soon. Sorry. Is that good?
Yeah.
Okay, so what is reactive development and what is domain-driven design? This is what we're talking about, and what's really an important question is when we introduce reactive programming, reactive software, what happens? So we actually introduce what's called uncertainty into our environment. This means that we don't know what is going to happen when, or if it will even happen. And so there are clear advantages to being reactive, but we're always choosing a set of trade-offs, aren't we? Whatever we do as software developers, we're always choosing a set of trade-offs. So what trade-off do we choose when we don't use reactive? Single-threaded blocking, the same old paradigm that's been available in programming since, let's say early to mid 1960s and beyond. But reactive is important these days because it avails software to the underlying hardware architectures that have changed over the past, 15 years or so, and that is to have multiple processors or multiple cores within a single processor. So in order to take advantage of that, you have to use threading, and threading is difficult, and so we look for ways to meet all these trade-offs and still use good design techniques, effective design, and that's with domain-driven design. That's what you're going to hear from me. So this is the basic idea behind the presentation. So if you look at any decent definition of domain-driven design, you'll see that this is kind of the essence of DDD. a bounded context with the ubiquitous language. Is anyone here completely unfamiliar with the term bounded context or the concept? So you're all kind of DDD aware. Yeah. Can I assume that by no hands shown? Okay. And the ubiquitous language. So if you have known about DDD for even the past 15 years or so, you know that bounded context and ubiquitous language are very important, and you'll even, if you ask Eric Evans about what is DDD, he will give you a definition sort of centered on this definition or this this concept of bounded context with ubiquitous language. So because we are using the bounded context concept, which means we sort of have a lot of models that are maybe somewhat related to each other but also independent, it means that we have multiple bounded contexts in any given system solution. So that leads us to the need to integrate between bounded contexts and collaborate with other bounded contexts. And how do we do that? Well, we do so through context mapping. And context map is, well, you could call this whole diagram a map, but a mapping is what is between any two bounded contexts that have some kind of association. And this mapping between them is a team relationship mapping, and it's also a mapping in the sense of how do we exchange information. So we have some patterns or tools around context mapping. So, in essence, DDD has not changed much in a long time. There are a few new tools around tactical or strategic modeling that have been introduced, but not that many. So, DDD could be thought of as quite a bit the same. One thing that has changed significantly is the use of domain events, and I think that although Eric didn't define domain event explicitly in Blue Book, you can still find evidence of events there. In fact, one is called handling event, and maybe you remember from the shipping example. And the handling event is when some kind of a container that's being shipped, across the seas or on a train or whatever it happens to be, is moved. So there is a handling of that container or cargo, and it's moved from one ship, let's say, to another. The cargo has been handled. And whenever that cargo has been handled, then a handling event is recorded. Well, it's become more of a first-class citizen in DDD since then. It's quite important, especially to reactive, because when we react to software, we're reacting oftentimes to events. So you can imagine events flowing between these bounded contexts here, and we have different kinds of team relationships, but one of the more information exchange relationships that we have is published language. And when we have a bounded context that gives a good definition of its language in terms of consumable information, one of the things that will be defined in that are the domain events that you publish outside of your bounded context and can be consumed by other companies. So imagine that there's probably a published language in at least one, if not all of these bounded contexts. So this is quite an important aspect. But what I really want to emphasize is that we've been talking about these concepts with DDD and teaching them and using them for like a decade and a half now, and yet it hasn't changed a lot. But what has changed is the environments in which we use these tools. So we've gone from on-premise hosting of container of some kind, and we've used web servers for quite a while, and we've used databases, of course, and web browsers, and so we have this distributed computing environment. But let's say we go back 15 years ago, it's really quite simplistic compared to today, where we have cloud computing, and we can deploy something into the cloud, and we may not actually really understand where it's running. We may be given an idea of a region, but do we actually know what data center it's in, and so forth? And that could change, on the fly. So that's distributed computing at a whole different level. And of course, our bounded contexts still have to interact, collaborate, integrate with each other. So this leads to complexity. I just wanted to make a few points about using domain-driven design. Recently, I've had some interactions with developers who say that they're using DDD, but they're really just using the tactical patterns, and any sort of understanding of the domain that they're working in comes from, basically a limited understanding, not really talking to domain experts. And I think it's fair to say that, you shouldn't just be collaborating as software developers, as programmers. You should be working with the business, and that is how you are really going to achieve insights into your ubiquitous language and the model that you create. So this is quite important. And the anemic model is really counter to the whole idea of DDD. So if you're using mostly getters and setters in your domain model, you're probably going to challenge yourself much more than if you just used fluent behaviors in your model. And what I mean by that is, instead of setting data that represents some, let's say, codification of a behavior, instead just have a behavioral method on your entity class, or whatever it happens to be, that says this is the behavior that's occurring, and we tell the object what to do, and the object responds to us or reacts to that method invocation or stimulus on it that says, we're doing this, and let it set the data the way that it wants to. One very important reason for this is, how do you publish or emit a domain event from your domain model if you're only calling setters? Do you put the domain event emission statement or expression inside one of the setters? Because you can assume that because I'm calling one of these, out of 5 setters, we're going to put that domain event publication in one of them. No, then where do we put it? Maybe in the client of the domain model? That seems like a really poor place to put the record that something important has happened in the domain model. So where do we put it? Well, we put it in a behavioral method that has a fluent name according to our ubiquitous language. And you solve a lot of problems, including line of code count. I challenge and assert that you will have more lines of code in an anemic model than you will have in a fluent, expressive, explicit domain model. So, and then try to test the anemic model. It's nearly untestable, or not completely testable, whereas with a fluent model, you can test it very thoroughly with just a few tests usually. Another thing to think about is putting good conceptual names around simple data for example, maybe a UUID or a big decimal. Why are we using a UUID? Is it because it is a business identity of some kind? It's a fairly, robust, guaranteed means to create a global unique identity. Well, why not put a type around that? An identity type. Name it. Give it a name. What kind of identity is it? Let's say, aggregate or entity does it serve as an identity for? Well, give it a name. And then any sort of very simple business logic that may be implemented by that identity can live on the identity itself. And then we move into something like big decimal in Java. If you've worked with this, one of the biggest challenges of using big decimal is the fact that you have to choose a scale factor, as in the number of places of rounding, and what is the business rule around how you round money, for example. Well, all that business logic could be stored in money, in a money concept, which we call a value object. And any math that we do on the value object is with another money. So if we want to add some money to a money, we pass the one money, a money as a parameter, and we say add or multiply or divide or subtract or whatever the operation happens to be, and then we are operating on money. And internally, of course, we're using a big decimal object, but externally, the client has a clear understanding of what they are using, and this is a money. Okay. Quite important, and along with fluent models using explicit behaviors, with what I mean by fluent is good names that actually read like you think as the business thinks, then this is a big step toward creating a useful model. And then I think there are all kinds of sort of a bit overblown interest in a new kind of persistence or a new kind of messaging. I refer to something now as the K word, that that Kafka thing. And it's not that Kafka is bad. I was just in Berlin last week, and I apologized. I said I promised myself that I wouldn't say Kafka in this presentation, but I had to say it to tell them what I wasn't going to say. So again, there's nothing wrong with Kafka, but is that what you need? It has some very good message sequencing, some very reliable kind of what you could say guarantees about the order of messages that are put into the store, and that's a good thing. On the other hand, some projects would really like to pretend that they are Google, Netflix, and Amazon all together, or one of those, take your choice, and they're really not, right? So choose a mechanism that makes sense for your project and is reliable and isn't going to give you headaches or not be supported in some way, but at the same time, don't use a very high throughput messaging mechanism, for example, just because you think it's cool to use. Just my opinion. So I've seen, just to give an example, I've worked on a project that was processing like 2 million messages per day, and one of the architects suggested that we have a Kafka topic with 36 partitions. Does that not have any meaning to you? Divide 2 million by 36, and maybe each partition is processing what would that be, like 50,000 messages per day. I mean, you can do that in 5 6 anyway. So, oh, now that I just trashed a bunch of products, I want to tell you about my product. Yeah, so I'm developing this this reactive platform called Vlingo. You can go check it out. Actually, this is the Java version it's open source. It's on github.com/Vlingo, and then if you add a -net to the end of that, that's a .NET edition of Vlingo that's being developed. Well, so I'm just going to talk about this to explain what a typical reactive platform, what getting into reactive development would be like. So typically what we're used to is in object-oriented programming, we have a client object and a client server. So when I'm discussing client and server here, I'm not talking about a remote client from a remote server, as in I need the network to talk to them. I'm talking about in VM, I have an object that is a client kind of object and a server object that provides some kind of service. Okay. So what do we do when we want to ask for the server to, we want to request it to perform some service? We invoke a method, and what happens on the client? We block. We do nothing until the server finishes. And that's, I think, what most of us have been comfortable with for as many years as you've been programming. This is very common. Okay, introduce the actor model. So I said that in reactive programming and taking advantage of the cores that are available on any given machine, the actor model is providing a much simpler way to use multiple threads. So to use all the cores all the time that are available to you. And the actor model is not new. And I'll show you in a few moments that it's really pretty old. And another thing that's pretty old is object-oriented programming. And the inventor of OO, which I think it's pretty okay to say that was Alan Kay, also the inventor of the Smalltalk programming language, actually talked about recently, well, several times recently, about his disappointment in how object-oriented programming actually turned out. It's not much like what he originally intended. He even says, which surprised me a little, that even Smalltalk didn't really turn out the way he intended. Well, mostly what he intended for object-oriented programming to be is message passing or message sending between objects. And Smalltalk was based on message passing. It was not asynchronous message passing unless it was augmented to some extent. But basically, an object could send a message to another object. And this was truly a message send because what would be sent is the what's called method selector of the method, which was sort of a it's known as a symbol. And this symbol, which is kind of like a string, but kind of like a hash tag string that was considered a constant. And when you sent this message, the Smalltalk would cause the method for that message to be looked up in a table. Let's just call it like a dictionary, right? And it would look in this dictionary to see, is there a method that actually handles this message? Oh, yes, there is. Okay, I'm going to dispatch to that method. But to the client, this was message sending. Okay, it's still blocked. But what Alan Kay said recently is that the actor model retained more of what I thought were the good features of the object idea. Okay. So the inventor of OO giving a strong nod toward the actor model, I think, is a pretty important thing considered. So this is what the actor model is. Before, notice that I rendered objects as squares or rectangles. Well, let's say that actors are really quite a bit like objects. They are objects, but I show them as circles just because that's different, and historically, you know, at least a few decades ago, probably 3 decades ago, a gentleman named Gul Agha, in a book about actors, an actor model, rendered his actors as circles. So I thought, hey, why not be consistent with that? So what happens with this object, a sender, and this object as a receiver, you could also refer to this as a client, and this is a server. When the client wants to send a message to the server, well, it sends the message. It has to know the address of this server or receiver object in order to send the message, but that's almost like having, you know, an object reference itself to the other object, and you just, you know, in essence, send it a message. In Vlingo, the way this happens is you literally invoke a method on an object, but that object is really sort of a proxy to the real actor object, and there's a disconnection between your invocation and the invocation on the asynchronous message sent. So it really looks very natural, like I'm programming in Java with methods, but it is literally a message sent. So we can represent that as an object that's being sent as a message, and this could be viewed as a command object. So we're telling the receiver, do something, right? That's what this blue message-looking thing with the exclamation point, the imperative, right? Do this. And that's the big difference between actor model and regular object-oriented, or what we know today as object-oriented. And the Vlingo platform provides several different components to it. One, you know, a few of them at a higher level are like authentication and authorization, directory, which is service registration and discovery, and streams, which is the means to store events in an event store, but also it's a means to stream those events or other kinds of messages around the enterprise. And then Lattice is a way to basically have a cluster of these actors that can send messages to each other without having to know where the actor actually is. The Lattice itself knows where the actor is and can relay the message. And there's some tricks with, you know, optimally sending the message in the first place where it ends up on the correct node. Very often as the first sort of message sent. Okay, and then actors can make great DDD aggregates because they form a natural transactional boundary, which is pretty much what aggregate is about. And notice how a controller, so even a UI controller, or what we call in ports and adapters architecture, a port adapter, can talk directly to an aggregate. We don't really need necessarily an application service or some sort of coordination to go on there. So we can actually eliminate layers and really simplify our architecture overall. And I can send command messages to the aggregate, and the aggregate emits domain events. Okay. And then, you know, of course, like I mentioned, we can cluster. So here are actors, and a Vlingo cluster node actually runs on the actor, on the Vlingo actors, and we have our servicer app here, and this may represent like an Vlingo HTTP. So maybe you want to have RESTful services available at, you know, at a client interaction level, but we can also stream events out to clients as well. Yeah, so here's a look at Vlingo HTTP. So services maybe talking to REST endpoints here, and internally, you know, that each each endpoint is potentially being satisfied. Tricks that can be played to optimize that a given REST request goes to one of these nodes that actually reduces the amount of network traffic to fulfill the actual message delivery. And like I mentioned, directory is about registration and discovery and of services. So basically imagine each of these services is talking to the directory saying, this is where I am. These are the nodes in my cluster, for example, and you can talk to any of us in this way by using these addresses. And then the directory receives those registrations and it broadcasts them out using UDP to other services who are subscribing to that broadcast, or it's UDP multicast, and they can find out where services are. They can reach them RESTfully or by some other means. Okay, and yeah, so I think you get the idea of that. So now here's what I'm thinking before we move on to this. With Vlingo, it's really my goal to make reactive programming a natural extension to the popular platform languages that are commonly being used. And right now, my initial effort is toward Java. I have developers working on a .NET version, which lags quite a bit. But so I want to make these available in at least the top 2 languages and platforms, as in Java and .NET, and make them easily consumable and very understandable by any developer that understands those languages and platforms already. Okay, so powers of 10. I don't know if you've seen an IMAX film. Have you heard of IMAX even? Maybe you call it EMAX. I don't know. But it's this kind of crazy, beyond peripheral vision 3D experience where you feel like you're there, but you're more than there. You're like dizzy from being there because your vision is completely overtaken by this presentation. But one of the films that they have is talking about, I don't know what it's called, it's Our Great Universe or something, but they sort of zoom in and out of in these powers of 10, and at one moment you're looking inside an atom, right? And then maybe a bacteria, and then out from there at a blade of grass, and then out from there you're looking at the Earth maybe, and then from there you're looking at a galaxy, and from there you're looking at many galaxies, and from there you're looking at a star being born. And it's just kind of mind-blowing to think about how similar, although different, but similar these powers of 10 are. When, so when I'm looking at inside an atom, well, it kind of could resemble a star being born. So what is this view right now? Is this a galaxy? I mean, maybe if you're a stargazer and you say, well, yeah, I recognize that part of some galaxy or whatever it happens to be. But, we could be looking inside an atom, or we could be looking inside a bounded context at the actors talking to each other. Or if we zoomed out, we could be talking about the different services in an enterprise, or we could be zooming out further and talking about the nodes on the internet, right? So depending on your viewpoint, there's a lot of complexity out there. There's not only a lot of complexity, but there's just a lot of moving parts. Imagine the uncertainty. I mean, if this is an image of, a snapshot of some galaxy, where is a meteor going to hit on some planet or into some star, some sun? And if it hits a planet, that could be a really big deal. If it hits a star, it's like, who cares? You know, it's just that meteor disappeared, you know, maybe several thousand miles before it even collided. So an interesting way to think about it. But, you know, now if you position your mind into thinking about, well, this could be the number of actors running on any one node or various nodes, how do we keep all this stuff running and working? You know, all the messages flying around. Think of the uncertainty. Well, one advantage that we have today with dealing with that kind of scale, even in a single VM, is that that we have the hardware to deal with it these days. And if we use the hardware correctly, we're solving big optimization problems or solving problems where we're not optimizing correctly. So I don't know if you're probably familiar with this quote by Donald Knuth: "Premature optimization is the root of all evil." Okay. Okay. So what's so important about that? You know, sometimes people can be correctly quoted and misquoted all at the same time. And here's my reasoning on that. You know what Donald Knuth actually said? We should forget about small inefficiencies. Premature optimization is the root of all evil. Having, using a language or a framework or any kind of programming model or paradigm that does not allow you to relatively, simply take advantage of the underlying hardware is leaving you with gigantic inefficiencies. I wish I could show you a video, but I ask you to look this up later. Go to YouTube and just search for CPU breakdancing. Okay, and maybe have you seen that? You know what I'm talking about? There are like 8 cores or 8 CPUs available, and there's one CPU that all these people are represented by, sort of like the Rapagangsta guys with, the hats on the side, and there's one of those guys out of 8 that's spinning on his head and doing, spinning on his back and doing all the breakdancing crate. And what are the other 7 breakdancers doing that are really CPUs or cores? They're all standing around going, "You the man, you the man, you the," right? No. You know what the actual point of it is? When you see the blue screen, that you see that this one CPU is hitting close to 100% utilization, and the monitor turns orange, and then, segmentation fault, right? And this is what a lot of software is running on these days. They're just allowing a big, available portion of the hardware to go unused. And so that's not a small inefficiency. That is a 7 times inefficiency, right? This is, if you want to talk about small inefficiency, we're talking about, I'm only using 78% out of the 80% that's available on a CPU, and I'm going to try to squeeze out that other 2%. Okay, worry about that after you're already using the other 7 available cores, to the greatest extent possible there. And here's another quote from Donald Knuth: "People who are more than casually interested in computers should have at least some idea of the underlying hardware, what the underlying hardware is like. Otherwise, the programs they write will be pretty weird." So now compare that to premature optimization is the root of all evil. But add that prefix statement that is, forget about small inefficiencies. Well, if you don't understand the hardware that you're running on these days, you are wasting a lot of hardware capabilities. From the year 1973 to 2003, so 30 years. And isn't it interesting that it was exactly 30 years between the time that Carl Hewitt, Dr. Carl Hewitt, first published a paper along with his colleagues on the actor model, and Carl Hewitt was running on hardware that was probably somewhere in less than a megahertz in speed and less than 10,000, maybe 6,000, 7,000 transistors on the CPU in the year 1973, and yet he saw that the future would hold the real definite ability to run across very powerful machines with multiple processors, which you could liken to cores, because they are all processors in their own right, and that networks would be fast, that networks would be more reliable, and so forth. So Carl Hewitt, envisioned this, and here's what happened 30 years after Carl Hewitt envisioned that. In 2003, right, Moore's law started failing. Moore's law said that every 2 years or so, we're going to double our processor power, including speed and transistors. And while transistors have actually climbed, right, more steeply than they had prior to 2000, processor speeds have leveled out. And here are a couple other situations that we face. So actually Moore's law proved to be in error to some extent, but in a good way, in that it was actually about 1.5 years when you could experience double processor power. So, right, we just kept improving and improving our chances to be successful with faster processors as programmers, and handle the greater increase in the amount of code that we wrote. And then all of a sudden, right in 2003, it starts, redlining, I guess you could call it, to the point where now it takes about 9 years to reach what we used to reach in about 1.5 years in terms of processor speed. Oh, and then after 9 years, what happens? Meltdown and Spectre. And then what happens? You basically lose the power gains that you had in processors. I don't know how many years we've lost because of those, but basically, we're just now the processors are handicapped in the sense that we're writing patches to operating systems and so forth that are trying to prevent these vulnerabilities from occurring. So we're losing power. Making a system call is actually maybe more expensive now than staying in user space. So and many times it is. So we're really in need of using cores. Cores are the answer to all these problems. It's our only hope. Obi-Wan, you're my only hope, right? It's I think we're at that point, and we need to start using cores to our advantage. So cores matter, right? Not much faster cores, but many more cores. In fact, on the Xeon 5 processor, you can get sort of a defaulted 88 cores on this processor. And if you go to a little, just a minor tweak that's probably going to cost a lot of money, but you can go up to over 200 cores on a single one of these processors. But okay, maybe that's not the kind of business you're in, but you can readily find 24-core processors these days on a commodity server. Okay, so we'd like to use Reactive to take care of those, and this opens up the possibility where streaming data can be basically partitioned off to different kinds of components simultaneously, as in parallel, and we're looking for the throughput. And right here, if you think about it, how how many cores are we using here? 1, 2, 3, 4, 5. When those are running, when those actors are running, right? So 5 cores out of how many? And they're each going to process maybe just one message at a time and then give up the processor and let another actor run. Reactive systems is what we want. So if we look inside any of these single microservices or bounded context, we're going to see this kind of actor stuff happening. But when we zoom back, maybe a power of 10, right? What are we looking at? Well, we're seeing multiple bounded contexts emitting events, right? These events outside the bounded context, and we have reactive at another power of 10. Okay? So now multiple bounded contexts are consuming domain events and reacting to them. And then what happens? Uncertainty. We love to think about things being in total order, and we love blocking. I mean, maybe you don't love blocking, but we're really used to it. But just this kind of activity that I'm talking about introduces uncertainty. I found this really great definition in the dictionary for uncertainty. You know, though, you can learn something from this statement. It is that uncertainty is a state. Do we know how to deal with state? We know how to deal with state. So we can reason about uncertainty, and we're going to talk about how do we do that. Okay, it's going to make us feel uncomfortable, it's unpredictable, it's riskiness, it's unreliable, it's chanciness, it's precariousness, it's all these, you know, it's variability and changeability and so forth, and we're like, oh man, why did I get into this reactive stuff, right? Well, not exactly. There are very good ways to deal with the uncomfortable feelings that we have with this. So, okay, we have an addiction to blocking. I've already pointed that out. We have an addiction to total ordering. Wasn't it Matthias Ferrari said his most famous tweet ever was the only hard problems with computers is exactly once delivery and total ordering of messages, and those 3 statements are intermixed and out of order, right, in his tweet. So yeah, that happens. We're addicted to ACID transactions, right? And not only ACID transactions, but you know, XA transactions, global transactions. We have a transaction manager that is going to make certain that, you know, not only these nodes, but all the persistent nodes on 5 other systems are in complete harmony at the end of the transaction. I mean, let's not mention that will take like 15 to 20 seconds to succeed, but, you know, okay, we're addicted to it. Okay, so we feel uncomfortable. It's okay to feel this way, and I'll explain why. Okay, so now I just want to say something just to reinforce a message that I'm trying to express. Our use of computing today is a matter of perspective, I believe. Okay. This image is called an audio stereogram. Okay, no, autostereogram. An autostereogram has an image inside this image that maybe you can see. Can anybody see an image inside that image? You see it?
It's a shark.
Yes. Good. And I do not know him. I've never, or I don't think so. And I didn't. Did I pay you any money to say that? Because other people are going, you must be nuts, right? You know, I think I was drinking some water at one meetup, and they said, I want to drink what you're drinking, right? There's a shark in there. There is a shark in there. So maybe if you stand back a little ways and you cross your eyes and you know, there's just sort of this way the tail is somewhere up here and its nose is what? Right around here? Is that true? Yeah. So it's in there. It's cleverly hidden, isn't it? You know what? This is a matter of perspective. There are cores in here. And if you just imagine, if you squint a little bit and maybe cross your eyes, you can see that there are many cores available. They're cleverly hidden, but we can make use of all of them. Okay. Okay. So now we start. How do we model uncertainty? Right? How do we actually solve these problems of things happen out of order? They happen many times or not at all. You know, when are they going to happen? One way to solve these problems is to build a fortress around your bounded context. And how would you do that? Well, we'll take a look. So think about our infrastructure. Again, this is a ports and adapters architecture. And on the outside here are our port adapters. This is the domain model inside and some application services that surround it. But think of this as the sort of really techie area. And again, this is pure ivory in here, right? Look, it's pristine. So this is where all the technology lives, or most of it. And when we see a domain event enter our bounded context into our infrastructure and a port adapter, we may attempt to do two things. We want to find out, have we seen this before? And we want to find out, is it in the correct order that we expect it to be in? Okay, so there are two patterns in a book called Enterprise Integration Patterns, and I can bet that most of you have read that book. And you probably are familiar with deduplicator and resequencer patterns. So deduplicator says, here's a way to make sure that you're not reading duplicate messages. And resequencer is, here's how to put your messages back in the order in which they were originally intended. So here's our deduplicator example. So we have actually three distinct events that we're consuming. Event 1, Event 2, and Event 3, but notice Event 1 shows up again. I mean, there are various reasons why this could happen. It may even happen on this side of the boundary, depending on our threading model. And so it could be that 1, 2, and 3 enter in the correct order. So we actually have Kafka, you know, we're using Kafka and we're like 1, 2, 3, they're absolutely in the right order. And then we distribute each of those 3 events to 3 different actors even, or threads. And what happens? One of the actors or 2 of the actors process faster than the other one, and they're actually consumed in an order that we didn't necessarily want to. Or even more tricky is that we acknowledge that because 3 gets consumed before 1 and 2, and we tell Kafka, yeah, we saw 3, and then 1 and 2 fail for some reason, and we never see 1 and 2 because we told Kafka that we've seen up to 3. So you actually have some really tricky infrastructure to implement, even to acknowledge to Kafka that things have been processed in the way that you know you want to make sure it does. But let's just take the sort of easier path, and this is, we see event 1, we see event 2, then we see event 1 again, and then we see event 3. And this can happen simply because we didn't acknowledge in time. Maybe we're not using Kafka, we're using, you know, Hornet MQ or RabbitMQ or something, and the messaging mechanism expected an acknowledgement within some time frame that didn't happen, and so it says, oh, they didn't receive event 1, so I'm going to resend it, right? So that causes the event not only to be duplicated, but to be received out of the original order, which could cause some other problems too. But let's just say we're going to deduplicate, and what gets through this deduplicator is event 1, 2, and 3 only. What does that mean? It means that when we first see event 1, we're going to persist some sort of indication that says, we've seen this. And then as every single event comes into our bounded context, we're going to have to ask this store, have I seen you before? I mean, there's considerable overhead in that. I mean, it may not matter to a lot of bounded context. Maybe the throughput is, you can easily, keep up with your performance needs using this kind of situation. But the other problem is, when is it safe to delete the ones that we've already seen? Is it okay to delete them after like an hour after we've seen them? Is it okay maybe 2 hours later, or the next day, or 5 days from now, or 7 days? The answer is, as soon as you delete it, you're going to see that event again, right? It's just that, I think that's called Murphy's Law, right? So think about that, and the number of lines of code, and the overhead, and the, we're trying to process stuff, and we're trying to use as little cloud infrastructure as we can get away with, because, hey, it costs us money. And then we have the resequencer. And this is where we see, right, we see event 3, then we see event 1, then we see event 4, and then we have some real latency, and then we finally see event 2. So out of order and latent. And here's what we actually want to achieve. We want to send event 1, and then event 2, and event 3, and then event 4 into our bounded context, or release those into our bounded context in the order that they occurred, because order is important to us. Well, here's what happens. So we have this look back that says, what have I seen? And have I seen things in the correct order? And because of the way that these are actually received, and 2 is latent, the only event that could be forwarded right away is event 1. But that's even if we understand that event 1 is the first one that should be seen in this packet, because we have yet other look back that proves that that's the event that we wanted to see, which means we need a very sort of definite sequence number or identity or something on each of these events that tells absolute order. So even getting another team to provide that on their events or any kind of message may be quite difficult in the first place. But then notice what happens. We're going to hold up events 3 and 4 until 2 is finally delivered. And what happens over here? Maybe the whole process that we're expecting to complete will not complete properly because we think nothing is happening. Right? We're just like, okay, we give up. And the big problem with all this stuff? It's hard. It takes a considerable amount of code. And you haven't solved any business problems yet. Think about that one. Right? Now, I made a statement today, and I usually do in my workshop, where I say, if you're trying to solve problems in this layer constantly, and you're always investing a lot of time in here, that's the wrong investment. You need to invest in this, and anything that you do here should be relatively easy to consume. So maybe it's the kind of mechanism that you have, or it's the attitude that you have toward this, toward the domain model, where the business is. And here's what I mean by that, right? We want to say, stop everything. Okay, it's all right now, go ahead, I'm ready for you. And the thing is, This guy says there is no now. Have you heard of him? That he gave a talk, Justin. Do you know him, Alberto? I don't know. But it's a pretty famous statement now. There is no now. And you know, now, in two places, in two APIs, local time now and date time now, they're a lie. As soon as you invoke the method and get an answer, now has changed at least maybe a few thousand times. And when you get the answer, it's wrong. It is not now. Okay? So we have to just sort of go, deep breath, you know, let go of sequence. Let go of timing. Let go of order. Yeah, so we're dealing with uncertainty. And here's the thing, right? I think we can all decide distributed systems are here to stay. It's a thing, right? And if you don't like distributed systems, maybe change careers. You really, you know, you just don't stand a chance in this industry unless you embrace distributed systems. Now, the problem with opening a restaurant is 2- or 3-fold. A restaurant's probably even more risky and more uncertain than distributed systems. And the other one is, if you open a restaurant, you're still going to be using distributed systems. You just won't program them, right? So, you know, just face it. They're gonna get to you at some point. So modeling uncertainty matters. The cores matter. The cloud matters. Microservices matter. Network and latency matters. IoT matters. We have thousands of these things, right? One thing that, you know, I gave this talk in a sort of a, you know, they're called Delivery Hero last week in Berlin. Do they operate here in Italy? Do they deliver pizzas and stuff to people's homes? And I asked the question, is it possible that you'll start putting IoT devices on pizza boxes to make sure that, you know, why have the driver constantly looking at their phone trying to figure out, am I on course for this? Where's my next turn? I mean, that, you know, the catastrophe in Tempe, Arizona recently with Uber proved that, right, that giving more control to devices and less control to your own eyes and awareness of driving is not a great idea right at this point in time. So maybe an IoT device attached to a pizza box can guide the pizza delivery person to your door much more safely. And if you make a wrong turn, then the IoT device may be able to direct you back on course and so forth. So it's interesting. Of course, you'll want to, you know, reclaim that IoT device when you make the delivery, because that's an expensive piece of hardware compared to the pizza itself. And all these things are relatively inexpensive, so it matters. Now, here's another thing to consider. Solid. Who here uses solid principles in their development? Right. So you've got you're responsible in this one project for like 100 classes, and you can go into those classes and you can prove that every single line of code aligns with single responsibility, or at least open close, or at least listcoff, or at least, you know, and dependency and inversion principle and so forth. And that's cool and everything. But you know where we're lacking most in the industry is the quality of the communication between objects. And again, this is what Alan Kay said, is that the really interesting thing about objects, let's say actors, is not how they're implemented internally. The interesting thing is the messages that they exchange between each other. So they have a quality name as an object, as two objects, and then do we have quality in the messages that we're sending around to these actors? And the quality of those messages is what the real world, other than we programmers, read. You know, truly, walk a business person up to one of those 100 classes and teach them about solid. You know, they don't give about solid, right? It doesn't mean anything to them. I mean, you can tell, you can explain, well, you know, this class is testable, it's, you know, all these things, and they'll say, why doesn't it work the way I said it should? Right? That is the ma. This is a Japanese word. Does anyone here speak Japanese? I actually have had a few people who speak Japanese in these meetups, and ma means roughly, it's a Japanese word that means the space between. Okay? The space between. So Alan Kay says the ma, the space between objects, is way more important, way more significant than the implementation inside. View an actor implementation inside, not as a place to just write bad code, because yeah, we don't want to write bad code, but it belongs to you as your own sort of little computer. Think of an actor as like a little computer, and it belongs to you. And who's going to tell you that your computer, you know, is implemented incorrectly? Well, most people won't even understand that. But if it receives an expressive message that reveals the intent of what you want to happen, and it conveys some sort of output, such as an event that says what did happen, wow, the outside world now can communicate with you, and they know, we know what they mean, and they know what we mean. Ah, that's valuable, you know? So I'm not saying don't use solid, but look, let's get our priorities straight, right? So we want to create reactive systems. Yeah, we know that we're dealing with uncertainty and it's a state. Oh, and then here's this guy, Pat Helen. You've probably heard of Pat Helen, and I referenced him in my red book. And Pat Helen wrote this paper called Life Beyond Distributed Transactions. So if you read Pat Helen's paper, and this is an updated paper, I think it's available on the ACM, the updated edition, which was updated just in the last few years or so. And Pat Helen, you know, describes what are called entities. And entities are basically DDD aggregates. The way that he defines them, it's basically a DDD aggregate. And Pat Helen says that, you know, well, one of his stories is he was hired into Amazon to make this hugely scalable system, and his expertise was in XA, global transactions. He wrote XA drivers for computer companies, and Pat Helen comes in and he tries to apply global transactions in Amazon, and it didn't work. You know, it just wouldn't scale. So he had to relearn and just about everything that he thought about persistence and transactions. And one of the things that Pat Helen says is about distributed computing and transactions that work is this. A system that can't count on distributed transactions has to manage uncertainty in the what? Domain model. Well, okay, I'm ad-libbing a bit, but the business logic. What does he mean? Well, in a DDD world, he's talking about the domain model. So what Pat Helen is really saying here is we are in the business of software that is distributed. It doesn't matter like what actual domain we're in. We are all subject to this environment of distributed computing. And therefore, you really have to care for this uncertainty that's naturally going to happen with these hugely distributed systems in the business logic. It's where it makes sense, okay? And this is what, in the paper, Pat Helen talks about activities. So in two entities in the Amazon system, Pat Helen refers to these two entities as having a partnership between each other. So something happens on entity A, and something needs to happen on entity B later. And we don't know if that has happened yet. We don't know if it will happen. And we don't know how many times it could happen. And we don't know the order in which it could happen. And so Pat Helen says, solve this problem with, I mean, he doesn't say dogmatically solve it with partner activities, but he says, here's an idea. Maybe you could use partner activities. Okay, so let's zoom in. I see this as maybe a model of partner activities that internally has a set of partner activities and individual objects of some kind. These are activities. And it's pretty simple, really, but basically we can record that an activity happened. So we're going to record that a partner activity was received by us. And this is an abstraction, an encapsulation. We can imagine that inside the activity we're describing more of what the actual activity was, maybe an identity or something. And we're creating a new partner activity and adding that to our activity set. And then later, you know, we can, as we're receiving a new activity, we can ask our partner activities, have we seen this partner activity before? And if we've seen it, then we don't want to do this again. And then maybe there's another one for ordering, you know, the sequence of things and so forth. Okay? And where do we want to actually do this then? Well, we're going to do it in the domain model. Now, I just want to say that I think this is probably okay, but and it would work. But the problem with it is it's not actually expressing anything about our actual ubiquitous language, right? It's not tied to what the business domain model that we are, you know, working in right now. It's generic. It's, you know, and this may be another thing that we end up putting on a boundary, and it becomes basically the deduplicator and the resequencer, or it can live within the entity, but, you know, it's just not connected to what we're doing. So could we figure out a better way in the domain model that's even less complex than the partner activity, and it fits our modeling language? So here's an example that we've been actually working on in the workshop. We have proposals that get submitted that describe a job that needs to be done, and there's a pricing calculator and so forth, and so these messages are flying all around, and these actors are in one bounded context, and these actors are modeled in another bounded context. All right, so there's this matching that has the proposal and the job, but there's the pricing that has the price calculator, let's say, and the price range and so forth, and there's also scheduling and fulfillment and maybe profiles and all these different bounded contexts, right? So where is the core domain? Well, we're going to say that pricing, the pricing engine, the algorithms and the rules really are our core domain. So let's, you know, think about that in this problem. And events are going to flow from matching. So this proposal submitted event will come from matching. So we have a client here that is sitting here outside the system, and they submit their proposal for a job that needs to be done. And the proposal submitted is emitted over to the pricing engine. And then the pricing engine will tell us, was the pricing denied? And if it was denied, what would be a suggested, you know, fair price, and maybe some other information, or the pricing was approved. I'm sorry, what? Oh, I thought. So the matching context will now react to that, and so we can see how bounded contexts are working together. Okay, so let's talk about how we actually can model a duplicate message, a duplicate event. And this happens to be an example of a commutative kind of operation, which means when we react to an event, it will have a non-destructive or non-error impact on us if we do it many times, right? If we apply this event many times. So what actually happens is we see an event from another bounded context, or many events from another bounded context, and we translate those events into commands, because the commands are part of our the events are part of someone else's language. So we want to speak our language within our bounded context, so we translate the meaning of these events into something that has meaning internally, and then we send those messages to an entity actor of some kind. And because it's a commutative operation, the operation basically said, you know, if you go back to your math days, and you, what the world was commutative again? Oh yeah, 3 plus 2 is 5, and 2 plus 3 is 5. And I can just keep adding 3 to 2 and 2 to 3 all day long and forever, and I'm always going to get 5, right? So if you have operations that work that way, they are naturally idempotent, naturally deduplicatable. It literally doesn't matter how many times you receive that message, it's non-destructive or non-error producing, okay? And so when you receive it, you simply hold the state that you have, and just looking at the state saying, for example, is it not empty? Is it a non-empty state or a non-null state, depending on the language tools that you're using? And you can simply say, okay, as many times as I receive this, I'm only going to emit a single event in response to the first one that I see. But I want to make certain that if I see this 100 times, I don't emit the same event 100 times. I just want to emit it once. And this is duplicate commutative, right? So we have some state, it's a simple state, it's in our entity. No, we don't need anything in our boundary with a look back, you know, database that says, okay, have I seen this before? Have I seen this before? We literally just absorb it into our model object, and we know whether we've seen it before because our state is either set or it's not. Deduplication of a non-commutative is maybe a little bit more challenging, but what it requires is that we have the means to uniquely identify the command, you know, that is derived from a domain event. So we need some kind of identity or sequence number or something here that tells us, have we seen this before? And if we've seen it before, we safely ignore it. It could be that the setting of our state is enough to indicate that. But if we have a complex state that is based on the potential of seeing several of these that are each applicable on their own, then we need an identity paired with each state transition that says, you know, I've seen this before, I haven't. But again, the goal is no matter how many times we may see this, we're going to emit just one event as an outcome. Okay, and then ordered sequence. This is going to really grab you here. I hope that this is completely underwhelming to you, because you thought that you were going to hear some magic, right? You were going to be like standing in line to talk to me after, going like, wow, and what about, and wow, I don't understand. No, this is completely understandable and entirely boring. And that's what exactly I want it to be, because it's simple. You don't have to do difficult things to deal with uncertainty. It's just get the job done, right? And here's the thing. This is going to blow your mind. Forget about order. It doesn't matter, right? Your entity simply collects the order that it understands that it has seen already, and until it sees each of the objects, it's simply not done yet. So if we see step 1 shows up as X, and step 3 shows up as Y, and 2 happens latently, right? Okay, we have one of 2 situations that can happen. 2 beats the clock, and we don't time out because 2 arrives in enough time. And when 2 arrives, we simply carry out, right, to completion. Okay, 2 arrived as Z, and we emit an event. Woo. No order necessary. If you can already take some intermediate steps based on step 1 and step 3 arriving early, regularly, then you can do that, and maybe you'll probably even emit some events that just talk about the temporary condition that you're in, but those may not be important to the outside world. Those may only be two finally finishes, completes, that we receive. Now we can finish the overall process and emit the event. The other situation here is that 2 doesn't show up before some time frame elapses and ends, and so we have to deal with this sort of incomplete process situation, but we treat that, we don't start rolling back the world now because that didn't happen necessarily. We may have to, but a better idea is to try to find a business solution to this. What is the business solution? Well, for one thing, maybe we just send it on to a customer service representative and say, something didn't work out here. Can you handle this with the customer? Or we send a message to the customer saying, okay, this and this are ready for you, but, and let's just say it's order processing, right? So this book and this book are available, but your new socks aren't available. They're out of stock. So would you like to receive the 2 books right away and just, you know, have the socks on back order, and your feet might be a little cold, or you may have holes in your socks for a few days, but we'll get them to you as soon as possible. And they go, yeah, I want that deal. Or you can say, or you can cancel the whole order, or cancel just the socks. What do you want to do? No, I'll wait on my socks. Okay. I'm wearing the same pair of socks for the past 3 weeks, but what's another few days? Okay, you can also calculate the closest. What does closest mean? Well, let's say that we are shipping product from an e-commerce purchase, and we want to know where is the warehouse that has this product in stock that has a relative closeness to the customer who has just ordered it. And so we say, you know, we fire off something that causes some processing to happen, and some warehouses, you know, emit events, let's say, and the events say, well, I have it and I'm within 0.5. I have it and I'm within 1.3, and I have it and I'm within 5.9. What do those numbers mean? It's just a scale. It might, you know, probably doesn't mean kilometers or miles. It's just, you know, something. But naturally we're going to say, well, we're going to go with warehouse number 1 or whatever as 0.5. That's the closest. So we can use that. We can also go for multiple choice, but what's the first or fastest? So we say, for whatever reason, you know, warehouse 1 may be closer and warehouse 3 may be closer, but we're not worried about closer now. We're worried about that warehouse 1 and 3 are so backlogged that they can't even reply to us because they're processing so much information, and warehouse 2 is just kind of sitting there, and they're maybe a little further away than we would like, but we want to have this on an airplane or a truck tonight, or, you know, first thing in the morning, and it's going to be delivered right away. So we can solve all kinds of problems with this and not necessarily care about the order, or we're just concerned that either we see what we need, a limited amount of data, or all that we need to see by some time frame. And obviously then, right, it could be that the time frame elapses, but what does this mean? It means that if you are in a time-sensitive process that has not completed or may not complete, you have to be able to schedule a way to look to see what processes haven't completed, as in this, you know, if we go all the way back here to step 1, 2, 3, if step 2 doesn't arrive within some time frame, we will simply receive in our actor a message that says, you know, interval signal, right? Something elapsed, and we check the interval or the type of signal, and we say, oh, okay, that means that we're out of time for this, and therefore I'm going to start some recovery process to make everybody happy, as happy as they can be, right? So time matters. And sort of the last few things I was going to point out is that I was asked by Rebecca Werkstrock, could you mention, first of all, that it's okay to feel uncomfortable and uncertain with, or uncomfortable about the uncertainty, but also mention some just general heuristics around where do you start and how do you do this? And so the first thing to make note of is you don't own the time frame, right? So if you try to make the time decision, this is what happens. Well, let's play the scenario of the CEO or the co-founder makes the time decision and it's wrong, and it really ticks off one of your customers, and you know, they yell at you and everything, and they write emails with all capital letters and all that stuff, and the CEO goes, well, you know, we were wrong. We got to tune that up a little. You know? If you make that decision, you get to tune up your CV, right? That's the difference. That's why you let the business make those decisions. It's not your decision. The other heuristic is, okay, you're going to be uncomfortable with this situation, but make decisions. You have to make decisions. Allow the business to make the decisions that the business needs to make, and you make decisions with how you're going to deal with this technically. But I think that it's pretty clear that you can use definitely a you know, a domain model, a modeling implementation of solving these uncertainty problems, at least in one bounded context. And then where do we start? You know, how do we figure out? Well, we start with what we know. So here's the thing with this matching and pricing thing. We know that matching needs fair pricing, and we know that matching is going to require a client to fill out, to describe what they need in a proposal, and they're going to submit that proposal. Okay, so now we can derive from that we can publish an event called Proposal Submitted, and when we publish that event, we can say that we want pricing to react to that in some way, and pricing is going to then consume that event, and it's going to tell us based on the keywords or some kind of indication of the job or task being described that this would be fair pricing for that. And so that's just one place to start. Now you can sort of unravel the rest of it by just taking the next step. What happens if the price was denied? What happens if the price was unfair? In other words, what happens if the price was accepted? Well, we also have to worry about scheduling. Is there a worker who can do the work on any, you know, do they have the time available? So we just sort of work piece by piece around this, and we solve this problem by what we know and then learning more, okay? So that's my talk, and I hope you enjoyed it, and I'm happy to take questions unless you just want to drink beer. And that's up to you, though.
Any questions? In the slide, when you said non-commutative events, do you mean that we should store every event that goes through an entity to keep it for later and see if it was already done? And if yes, doesn't it create less storage?
Yeah, so, well, okay. The answer is yes and no, but here's the thing. What you really need to store is, if you have a single state, maybe the state itself makes it commutative because you can simply look in the state and say it's set. But what this implies is that you may have multiple states as in a collection, right? That needs to be individually identified. And if you see another command arrive at the entity, and we look at our own internal collection and say, I've already seen that identity, then we know that we've seen it before, and we simply don't take any action on it. But the real difference between these two is, right, one is based on only this says open. And I have an open state. Well, I don't need to process this again. But if my state is closed and I see open, well, it's kind of clear I need to handle open.
And we put this actually with the ID.
Yep.
If there will be a lot of events going through an entity, so the number of IDs will be huge at some point in time, or maybe missing a point.
No, I don't think you're missing the point. That's possible, and Pat Helland even says it could be that the state of an entity grows quite large, and you'll have to be able to deal with that. But then again, you could ask yourself, if my entity state could become that large, because it's not just a matter of the identity. There is an associated state with that. So you're only keeping the identity to identify that the state has already transitioned because you have seen this message before, right? Which means that if your state's going to, in what you're describing, your state's going to become huge anyway, even if you don't hold identities, just by holding the state itself. So maybe you have to ask yourself, is my entity, modeled correctly? Maybe I have another concept or more than one concept that should be handling these different states, right? Yeah.
These entities are persisting somewhere.
Yeah.
The entity of the domain model.
Yeah. So I don't remember where it was, but somewhere here. Yeah. Well. So anyway, there is an event store. I don't know. There's an event store somewhere that, it associated with your bounded context that is storing these events to look back at. Where was it? Maybe it was here. I don't know. Anyway, there's an implied storage here that's storing the state, yes, of this, and it could be state that's based on an ordered collection of events, or it's a state that is serialized from the object itself. Right? Okay. All right. Thank you. Oh, we have to give away the book, so I'm going to let.
Thanks, Vaughn.
Who's going to choose? Who's going to choose?
I had another one, not me.
Okay.
So I wouldn't get the single word.
Alberto's.
Who's excited? Oh.
Let me take a picture. Why would
From the salad.
we take a picture?
So you're choosing that one. Oh.
Filippo De Petto.
Grande.
Questa cosa mi ha fatto pensare che non siamo ai mondiali.
There you go.
I get signed.
Thank you.
He's like, no, I don't want to sign it.
No. There you go. Bomba. So there's beers and pizza waiting for us. So we'll go there in a second. Let me take the photos first.